I'm happy. I was stressed because I was like, he didn't put them in the grade book.
I did about 10 minutes ago.
Oh, okay, so I
20
haven't
minutes
gotten the.
Yeah. And you two are both still sitting comfortably in the A range, obviously, so. All right, so what we're gonna talk about for the rest of this, of the lecture portion here,
Yeah,
is going to be two classes of reactions. They're kind of gonna be fundamental to a lot of what we're gonna see going forward. So specifically, we're looking at, not sure why it's not, there we go. Substitution and elimination reactions. And they're really good, sort of like we use cyclohexane as an example for studying all of like conformers and things like that. Substitution elimination is a really good first mechanism to learn. Because they're very well understood. And we know them in a lot of depth, and also the actual products are pretty straightforward. So it's the trickiest thing we're going to run into is that these substitution and elimination reactions are competing reactions. So under some conditions, you'll get a substitution reaction with the same reactants, but different conditions, you could get elimination. So that's something that's has some subtlety to it. So that's why we're going to start with substitution elimination reactions. As first off, does anybody have any questions about the exam?
no. Okay, when I was doing this one, I felt like I wasn't sure with what I was doing. Part B. Can we talk
Yes.
about that one?
Yeah, let me draw it up on the board and then I'll hand you that back.
It's S. I did the same thing.
Does it matter? Oh, yes. But on the back, I was all, this is R.
And is it that where the OH is?
Yes. I think so.
What did I do? I did this.
Yeah. So
The hydrogens on the end can't interact with anything.
yeah, the hydrogens are never going to be part of a resonance structure, so they're there just to show that they're there. So your first resonance structure is going to be if this little oxygen pulls the electrons towards itself. And you get the negative charge now because the oxygen had 2 lone pairs and 2 bonds. Now it's got 3 lone pairs. And your charges still have to add up to 0 since you started with something neutral. So that's your hint that because you took electrons from this carbon, it's got a positive charge here. Then the other ones are just going to be leave this alone. And it's going to be move electrons towards the positive charge. So there's that one. There's that one, and then the last example is when you have one of the lone pairs on this oxygen moved down. So your final resonance structure will look like this. So there's a total of 5, including the one you started with. This first one is going to be the most stable because no charges. Right. And then the last one we drew is the second most stable. Because you do put a positive charge on an oxygen, but everything still has a full valence here. So most significant second, and then these ones, they're all these two are both gonna be probably close to the same, but I would say this one's more stable than that one, because that puts a positive charge right next to a lone pair, so that's not gonna be very stable, and then this would be the least stable. Because you've got an incomplete valence directly next to a negative charge. But what I was looking for the most is where you're 1 and 2. If you called 3, 4, and 5, if you said they're all approximately the same, I wouldn't have marked you down on that one. What I was really looking for is this is the most significant, followed by this.
No, I just missed, did you do this? Did you miss that too?
This is a triple. This one.
Riley got the cis. Even italicized it, I noticed.
Yes, thank you.
The,
And both of you had the same problem, the Newman projection, you both drew the S
I
conformer.
think I drew it and like made sure I was looking at the right one.
So let's see here, 1. You got your priority backwards.
I thought,
That's 2, that's 3. So 1 is bromine, but then the rest of the big group is gonna win the tiebreaker. They both go to a carbon first, but then this carbon can only go to a hydrogen from there. This has another carbon attached to it.
oh, okay.
So that's why you got the wrong one, is because you got your priority backwards.
This one. Was it another priority thing for me?
Yes, and that's. It looks symmetrical both directions around this, and I think you both might have done the same thing. When in doubt, the more complicated side is gonna have priority if everything else is equal.
That's
So
what I
this one
figured,
would
was
have
that
Yeah.
since it had the double bond, I
Yeah.
was like, I'm just gonna say it takes priority.
Yes, we did not spend a ton of time on that, but basically the pi bonds allow you to use that direction again
I
without
was just looking at
repeating.
like this side is CH2 and this side is CH2CH, so it was like less H's, so.
Good logic. So I mean, it was not a big deduction, because that isn't one that we spent much time on, the double bonds. But you guys,
Okay.
you did
Number
great
7
on-
was tricky. I'm honestly surprised I got it all right because I was double guessing myself between 3 and 4.
So the tricky one, yeah, the cyclohexane is tricky. Because but this one, it's gonna be trans in both cases. This one goes through a chair flip and spins around, it looks like that.
Right.
So you did good.
Yeah. But then this one I was counting and I was like, they both have the same number of carbons and hydrogens.
That's literally.
That's the tricky one, right?
Yeah.
They're constitutional isomers,
Yeah.
but because one has an ethyl group and one is dimethyl, that's your
They're
distinction.
not the same.
Yeah.
What's your wash?
Well, I got that one wrong too. I said get larger because the temp is going lower, but I don't
The
think that
equilibrium
was right.
constant would decrease, and then I explained my why, and my why is wrong, but I know it, I just don't know why.
So let's look at that one. So we'll do it on here, so it's on the recording.
Okay.
Delta G is delta H minus T delta S. Right, so if delta G gets more negative, that increases the equilibrium constant.
Right.
This one's already positive, which means unfavorable, right? Favorable. Delta S is favorable, right? Because it's greater than 0, which with the negative sign means so if this term, so if the favorable term gets bigger, K gets bigger. Or sorry, if the favorable term gets more negative, then that means that K is gonna be larger. But in this case, is temperature decreases, right?
Yeah.
So if temperature decreases, our favorable term gets smaller.
Okay.
If our favorable term gets smaller, that means the reaction is less spontaneous, which means a smaller K.
Wait, so I don't understand why my reasoning is wrong. It got smaller because the temperature decreased.
Because you just redefined the term, you just restated the problem. It's, you didn't explain it in logical terms, you just said it got smaller because it did.
Yeah, that's what I did too, but that's because I didn't study that part very well.
So I was looking for
I-
something along the lines of the, I'm not picky about the language, but the way that I find it easiest to say is the favorable term gets smaller when the temperature went down. If these were backwards, if the favorable term was delta H and the unfavorable was delta S, then we'd have the opposite result, right? That's what the practice test was.
Yeah,
Had those two signs flipped.
but I took your advice and studied the rest of the page and it worked.
You know, I just kind of looked over my practice exam, and by the time I got home from the trunk or treat and did things for Sunday, I went to bed and I was sick. Let's see. Even when I only had a day.
We're gonna spend more time going over this whole quarter, right?
Did you get it wrong?
Yeah, okay, I'm not gonna ask then.
So what you were missing is that those were two steps.
Yeah, in
The first of which was the nucleophilic attack. The second step was leaving group leaves.
Oh,
See?
okay.
Each arrow is its own step.
Correct. And when you put the arrows all together, you get something, you get the net reaction. All right, so this next substitutions and eliminations are also really good because all four of these steps play a role at various points. We're gonna start with the simplest ones, which are nucleophilic substitutions. Nucleophilic substitutions. Which we abbreviate as S sub N. Is for substitution nucleophilic. And then there's gonna be two versions of it, SN1 versus SN2. Has to do with, is it first order or second order? Do you remember what second order means?
Does it have to do with the bonds?
Nope.
Then no,
I mean, everything has to do with the bonds technically.
but it's not like what has the strongest bond.
No, so there were first order versus second order, we're talking about rates. So in a first order reaction, only one of the components affects the rate. In a second order reaction, you need two things to run into each other. So there are two different factors that go in, two different concentrations that go into affecting the rate. So in a first order reaction, so let's say our reaction is AB plus C goes to AC plus B. The classic version of a substitution. Basically, you swap out one of the groups on your starting molecule. If it was first order, it might be something like rate equals rate constant times your concentration of AB. If it's second order, be something like rate equals a rate constant times your concentration of AB times your concentration of C. So the difference between first order and second order is how many pieces are in the rate law. So if it's first order, it doesn't matter what your starting concentration of C is. Because your slowest step only involves AB. If it's second order, then you can change the concentration of either of these and change the rate of the reaction. And what that tells us is that C must run into AB in the slowest part of the reaction. We'll come back to that. I just wanted to remind you of those ideas of rates.
I'll go over my old notes when I get these.
All right, so we're also gonna talk about these reactions in the context of a new functional group. It's not really a new functional group, these alkyl halides.
Yeah.
We've dealt with them a lot, right?
Yeah,
We already know how to name them, but they're gonna be the reactive group. The most common reactive group in a substitution reaction. If you have an alkyl halide, it's a good leaving group. Because it's stable on its own and it's more electronegative than carbon. These other two versions, aryl halides, and vinyl halides.
Yeah.
That's when you have a halogen attached to a double bond, something with a pi bond. Those have their own class of reactions. Those aren't going to react the same way as our alkyl halides.
And you said alkyl halide is a good leaving group because it's stable on its own and more electronegative than hydrogen,
Than carbon.
than carbon.
So, and these alkyl halides basically have two reactions that they go through really easily. One is a substitution, whereas because your halide is a good leaving group, something that's a strong nucleophile can come in and basically boot the halogen off. You just replace the halogen with something that's a better nucleophile, that is a better at attacking positive charges. And your net reaction though is always going to look the same. Your halogen leaves and you replace it with a nucleophile. And a nucleophile was one of those terms we added at the last minute. Either you remember what a nucleophile is?
it is very electronegative.
Good. Why? How do you know that?
Well, it wants to like steal hydrogens, right?
Yeah, it means it's good at attacking positive charges, right?
Yeah.
That's what nucleophile means. So something that is really electronegative is gonna have a partial negative or a full negative charge, which means it's gonna be more attracted to a positive charge.
It means it's good at what?
It's good at attacking positive charges. Which also means you mentioned H pluses, Riley.
Yeah,
Technically, something that's good at attacking H pluses is a good base. But most cases, a good base is also a good nucleophile.
Oh yeah, isn't this like opposite of pH? Kind of situation?
Yes, we use that pKa table. And the more negative something, the better base something is, the better nucleophile it is usually. Our other version of an alkyl halide reaction is if you put it with a strong base, you can essentially kick the halide off still, but you're gonna make a new pi bond between two carbons as a result. So it's called an elimination because you're removing things from your starting material. Basically, if you draw a hydrogen in here, from your starting material, if it's an elimination reaction, you're gonna lose an alkyl halide and lose a hydrogen. And that results in making something with a pi bond. Now, this is a little bit weird because we just got done talking about how a good nucleophile also usually means a good base, right? So that means you can actually have the same reactants and have them go through two different reactions. Because if something is a good nucleophile, that generally means it's also a good base, which means both of these reactions are happening simultaneously, which is what we call competing reactions. So we're going to focus on substitution reactions today. We'll add elimination reactions in more detail. We have a whole lecture just on, here's these 4 new mechanisms we learned. How do we determine which one is most important? But first we have to learn those mechanisms so that we can figure out what variables help control which way it goes. Be like in our analogy, altitude analogy, be like if you have more than one way you can leave the basin, which way are you going to pick? It's going to depend on the conditions a little bit, right? If I'm trying to get to Reno from Incline Village, if the weather's nice, I go over Mount Rose. If it's not, I might go south and go around Spooner.
Yeah.
So the conditions dictate which path you take, even if you're going to the same product. All right, so first steps first, so let's just practice drawing what the product of the substitution would be. So we have our alkyl halide. What's our nucleophile going to be in this case?
I don't, the chlorine?
Chlorine's already attached to our carbon.
So it's halogen leaves and replaces nucleophile, not.
The nucleophile is going to replace the halogen, yeah,
Halide.
halide, technically.
Are they, what's the difference?
Halide has a negative charge or is bound to something less electronegative than itself.
Or is it the whole thing?
So what is this, when we break this compound up, what is it?
Sodium and alcohol.
Sodium, ion, not just alcohol. That's what the functional group would be, but when it's just part of an ionic compound, that's hydroxide, right? So out of sodium ions or the hydroxide ions, what's going to be a better nucleophile?
The hydroxide.
It's got a negative charge, right? If I'm being really picky, then we want to make sure that we put our negative charge on the oxygen, not on the hydrogen. When it comes to drawing our mechanisms, that's going to be important. So then our product is just going to be, okay, replace the halogen with our nucleophile. And we get the halide. What else is still around? Sodium. Or so. So the sodium ions are basically there as a spectator ion, right? If you remember that term from Gen Chem.
I don't, but I understand. We learned a lot over the last year.
It's true.
Expect me to.
So
remember.
it's a whole year-long course. It's called a spectator ion just because it doesn't do anything. So we use that term. I guess I don't know if you use that term that term usually gets used when we're talking about precipitation reactions back in 102 probably, when you first learned reaction types. Actually, that might have been the end of 101, so a while ago. Right, so that's all there is to drawing the product. If it just says draw the product of this reaction, we're done. That's it. What about if it goes through an elimination instead? If the hydroxide acts as a base instead of a nucleophile.
The opposite, wouldn't it?
Not quite. The elimination means we're gonna make a pi bond. So we're still gonna be the chloride is still gonna leave. The sodium ion is still gonna be a spectator ion. In an elimination reaction though, that nucleophile acts as a base, meaning it's gonna accept a proton, not attack a carbon, it's gonna attack an H plus. So the chloride is gonna leave. And you wouldn't need to draw this entire mechanism in order to answer this question, but just to tell ourselves what's gonna happen here. If the chloride's gonna leave, and the hydroxide is gonna steal a hydrogen to become water. I'm having trouble with my words today. So we're gonna make a water molecule, and then what's left? When the chloride leaves and the hydroxide steals an H plus, the electrons that were part of the carbon hydrogen bond move over to make a pi bond. So two of the hydrogens are still there. One of them got pulled off by the hydroxide. And the chlorine's gone too. So your net result for an elimination is always pull the halide off and pull a hydrogen off of one of the adjacent carbons. And then make a pi bond. So this is the same reaction from the previous two slides. You put 2-chloropropane into a solution with sodium hydroxide, we're gonna get elimination as well as substitution happening. And you'll notice this is not balanced. In organic chemistry, a lot of times when we write out reactions where we have more than one possible product, we oftentimes, it's not gonna look balanced unless you consider the fact that you don't have a 1-to-1 ratio of either of these. Right, so even if this is a major product, that might mean 75% of your carbon product is the elimination product, and 25% is a substitution product under these particular conditions. As long as these percentages add up to 100, then we can still consider this to be a balanced reaction. Right, because it's like, okay, if I started with 100% and I made 75% and 25%, that still adds up to my total amount of carbon that I started with. And the way we describe that, especially when we don't want to put actual numbers to it, is major product versus minor product. Similar to the way with the resonance structures, we didn't try to put like a percentage to it. We just said most, second most. Major product just means what you make the most of, minor product, and you can have more than one minor product. And or you can have two products that are formed roughly 50-50. It's gonna depend a lot on the conditions. And that's why we're gonna spend so much time with that, is determining which is the major product and which is the minor product is kind of tricky. All right, so why do we see these reactions mostly with alkyl halides? Well, for the most part,
Electronegativity.
negativity, and the electronegativity means it's a good leaving group. So remember how, we can track everything back to the electrons, right? In electronegativity. In this case, the alkyl halides are the most significant group that goes through these reactions because of their electronegativity. And also because of how they can be stabilized when they're in their conjugate base form. So we're going to talk about that as well, because oxygen's pretty electronegative too, right? So oxygen should also be a good leaving group. But it's not as good as the halides, despite the fact that the halides actually are less electronegative. So there is something else beyond just the electronegativity going on. Because if it was just electronegativity, oxygen would be a better leaving group than all of these except for fluorine. And so there's more to it, basically. And it has to do with the size of the atoms, and it has to do with what other groups are around. Are we doing this in water, or are we doing this in ethanol, or are we doing this in a completely nonpolar solvent? Will affect some of these leaving groups as well. All right, so in general, whatever is a strong acid, its conjugate base is a really good leaving group. And our simplest strong acids were hydrochloric, hydrobromic, hydroiodic, sulfuric, and nitric, right? Those were our strongest acids. Sulfuric, so there's a list of, I think there's 6 of them that we teach you in Gen Chem.
Okay.
It's hydrochloric, hydrobromic, hydroiodic, perchloric, nitric, and sulfuric are the ones that we teach you as those are the strong acids. They're the ones that are the most common to see. But the simplest of those are hydrochloric, hydrobromic, hydroiodic. We're going to add sulfates and nitrates later on.
And these are
Strong acids.
strong acids, so their conjugate bases are the leaving groups.
Are the leaving groups. And if they're strong acid, that means that they're really good at being stable. The conjugate bases are really stable on their own. Right? This is a way, so whatever you have, if it's the strongest acid, that means its conjugate base is the most stable base. So it's the most stable on its own, which means it's the better leaving group. Right, so I told you that these tables were gonna keep coming back in terms of pKa.
Yeah.
Because it's a really good way of remembering what's a good leaving group. Is in addition to just acids and bases, we also need to think about it in terms of nucleophiles in leaving groups. So something that's a bad leaving group makes it a good nucleophile or a strong base. If you look at all of our alcohols and waters, they all have that pKa in that 15 to 18 range. So basically, oxygen is not a great leaving group. It means they're pretty good nucleophiles, pretty strong bases. But our least stable base, our strongest base, and our worst leaving group is when we switch to being nitrogen, not even oxygen at all. So the halogens were all really good at being leaving groups. Oxygens are bad at leaving groups, and the worst leaving group is a nitrogen.
The bad leaving group good nucleophile.
A bad leaving group is a good nucleophile. Exactly. So with that in mind, which of these has the better leaving group? The bromine is a better leaving group. It's higher up on our chart here. Bromide is stable on its own. Hydroxide is not very stable on its own. So it's all the way down here. This winds up being important because if I go back to that slide with the substitution reaction, the reverse reaction is also a substitution reaction. If this reaction happened backwards, we'd have chloride coming in and attaching to a carbon and the hydroxide leaving. That's also a substitution reaction. You broke one carbon bond to something that was a good leaving group, or is a leaving group, and you replaced it with something else that acted as a nucleophile. So one of the reasons that these pKa tables is important is because it allows us to predict which side is going to be favored at equilibrium. If both reactions can happen, it can do a substitution reaction forward or a substitution reaction backward. How do we know which side is going to be favored at equilibrium? We look at these tables.
So a strong acid is a good leaving group.
So a strong acid means the conjugate base is a good leaving group.
So why is bromine's a strong acid though?
So it's a strong acid, so its conjugate base, which would just be the bromide, is good at leaving. Hydroxide, water is not a strong acid. So its conjugate base is not a good leaving group. Right, and we always want to think about what is the conjugate base, because there's a few cases, water in particular, it's tricky because water has a pKa of 15.7, which means hydroxide is not a great leaving group. But hydronium, which is just protonated water, its conjugate base is water. So water is a good leaving group because it has a negative pKa. So water is a good leaving group, hydroxide is not. And that's tricky to remember because that's water right there.
Yeah.
But it's actually referring to the conjugate base, which is the hydroxide. So if we looked at fluoride versus this oxygen with a positive charge, now which one is a better leaving group?
The oxygen with the positive charge.
And in this case, our leaving group is water, not hydroxide. So that means we're up here. And we're comparing it to fluoride as a leaving group. What this means is we can actually control how good of a leaving group some of these are just by controlling the pH. If we put it under acidic enough conditions so that we can protonate an OH group, we can make it go from a pKa of 15.7 to a pKa of -2. So under basic conditions, alcohols are really bad leaving groups. OHs are really bad leaving groups. under acidic conditions, we can make them good leaving groups. All right, so let's talk about how the substitution reactions actually happen, because that's going to give us some insight. So one of the first, there are two possibilities that they were looking at when they first were trying to figure out the actual steps involved. Is there's really two things that have to happen for a substitution reaction. Your nucleophile has to attack and your leaving group has to leave. The second way that this can happen, though, is what's called the stepwise mechanism. So if there's two steps that have to happen, there's two possible ways to do it. You can do both steps at the same time, or you can do one then the other.
So the concerted is when it happens at the same time.
Correct. Concerted means all at once. That's just a good English vocab word. And stepwise is the sciencey mathematical way of saying step by step or one step at a time. So if these two steps happened, if they happened in two steps, but it still has to have a nucleophilic attack and still has to have loss of a leaving group, which step has to happen first?
That was gonna be my question for you.
Okay.
Well, does the leaving group have to leave first to make space for the nucleophile?
Bingo. If we started with a nucleophilic attack, we'd be making another bond to that carbon. We'd be making a carbon with 5 bonds, so we can't do that. So if it's going to be stepwise, it has to be loss of the leaving group first. And that's going to make an intermediate. And that intermediate is going to be a carbocation. So it's still leaving group leaves, nucleophile attacks, just in 2 steps instead of all at once. So how do we figure out which way it is? Well, we have 2 options. If we're trying to figure out which one is the correct
If
way.
it's concerted stepwise,
Mhm.
I have no guesses on this.
Let me clear this. Because it has the more clean drawing. So if your leaving group leaves, nucleophilic attack happens. If we want to know which way we could figure this out, just based on looking at these steps, if this is happening in a concerted manner, you need a nucleophile to run into the carbon that has the leaving group, right? You can't have a reaction if they don't bump into each other. Right? Versus if it's stepwise, the slow step is actually just your leaving group leaves. Once you do that, you make an unstable intermediate. If you think about what the potential energy surface looks like here, You're gonna start relatively stable, you're gonna make an intermediate that's uphill in energy, and then make something, a final product that's downhill in energy. So going back to our potential energy surfaces for the test, this first step is harder, is slower than the second step.
Yeah.
So that means that our loss of our leaving group is our rate determining step. That's the one that's going to determine our overall rate law. And our rate determining step is your leaving group leaving. There's only one molecule involved there. Which means if it's stepwise, we should see a first order reaction. If it's concerted, we should see a second order reaction. So the concerted mechanism for this reaction is what we call SN2. So SN2, substitution, nucleophilic, second order. And its rate law should look like this. If you need your alkyl halide to bump into the nucleophile before the reaction happens, then changing either of these concentrations is going to make it more likely for the reaction to happen, which means it's going to happen faster. Right? If I doubled my concentration in nucleophile, I doubled the odds that they run into each other. If I doubled my concentration of alkyl halide instead, I still double the odds of a reaction happening. So they both are affecting my overall rate. All right, so that means it should be pretty easy to figure out. If you change your concentration of your nucleophile, if your rate stays the same, then it has to be a first order reaction. But if you change your concentration of the nucleophile and the rate changes, it has to be second order. It has to be concerted. So remember back when you first learned rates, do you remember doing the method of initial rates? Which is basically you do a reaction and you measure how long for it takes the reaction to happen. And then you double one of the concentrations and you look at how long it takes for it to happen, right?
Yeah.
That's all we would do here. Set up the reaction, find some way to measure when it's done with a color change or something. And you get a baseline reaction time, and then you change your nucleophile concentration.
Sorry, if the nucleophile is changed and the rate does not change.
That means it can't be part of this reaction law, this rate law.
Making it stepwise or concerted?
Stepwise.
Okay.
All right, so our two options are, if it's stepwise, then your rate is just going to be equal to K times concentration of alkyl halide. Because your slow step is your halogen leaving. And then your nucleophile comes in and that second step is really fast. If it's concerted, that means that both of them affect the rate. So the first part looks the same. But then it also has that second term, the nucleophile concentration. So if we change our nucleophile concentration and the rate changes, it has to be concerted. If we change our nucleophile concentration and nothing happens, that means it's not part of the rate law, which means it has to be stepwise. In both cases, changing the concentration of alkyl halide affects the rate. So it's part of the rate law no matter what. So they did that test back in late 1800s, probably. They're figuring this out, which is really impressive when you consider it's before they even knew what an orbital was or how electrons behaved. Makes it all the more impressive the way they figured this out, because they just said, okay, well, let's test the reaction order. And they found that it was a second order reaction where your alkyl halide and your nucleophile mattered. So NU, just our shortcut for nucleophile, just like we have ME is for methyl. But what they found also was that if you added methyl groups on the carbon that had the halogen, it slowed the reaction down. So now we're not comparing the same reaction to itself. So it's a little bit trickier. It's not just looking at method of initial rates. But what they found is if you had a methyl group with a halogen attached, it was much faster than if you had an ethyl group with a halogen attached, which was in turn slower. So methyl was faster than a primary carbon having a leaving group, which was faster than the secondary carbon as having the leaving group. So where are we going with this? We'd expect the tertiary group would be the slowest. What does that tell us?
Things directly bonded to the carbon don't want to, right?
They don't want to leave. And it also basically means that that if we look at what these shapes look like, it's a lot easier for your nucleophile to come in and attack here than there. In both cases, you're gonna have the same steps. Your leaving group leaves at the same time as your nucleophile comes in. But having extra stuff in the way is gonna slow it down. And this last factor is really interesting. If you start with a single stereoisomer on a chiral carbon, you only get one stereoisomer as your product, which is what we call stereospecific. The reaction is stereospecific. If you start with R, you only get S as your product, which is weird. Because it means basically, if you look at the two possible ways you could have your nucleophile attack, it can't be both of them. Because if it approaches from side one, if you start with R, you're going to end with R. Because you're just basically bumping off your leaving group and replacing it in the exact same spot, right? But if it comes from position 2, now when your leaving group leaves, this whole thing is basically gonna be reversed now. We went from R and now we're S, because these hydrogens are gonna pop to the other side like an umbrella flipping inside out. So how do we determine which of those makes more sense?
2.
Why?
Because one is just the same thing. So why?
So we would want to
waste
do,
energy?
we would want to do the test, say, okay, if we start with R, do we get R back? Or do we start with, if we start with R, do we get S? And what they did find is that route number 2 is preferred. And
Well,
for
it
one of
takes
the
less
reasons,
energy, right?
why?
Because it doesn't have to bump a group off.
It's the group is still gonna get bumped away, but remember that our nucleophile is a negative charge, right? What's the charge on our leaving group? Why? If it's a leaving group, it's more electronegative than a carbon, right?
Yeah.
So if we've got a partial negative here. Does it make sense? Is this negative gonna come in right up next to the other negative?
It's like magnets.
Exactly. So even though this is where our partial positive is in both cases, our nucleophiles are going to be attracted to the carbon in both cases. If there's a way that it can be opposite of the other charge, that's gonna be preferred. Especially when you consider that most leaving groups are fairly large. So even beyond just the charges, the sterics, which was just our way of saying how much space there is, right? The sterics seem like they should favor position 2 as well. Which also kind of explains this.
Yeah, but the methyl groups are gonna make the sterics bigger.
Exactly. If we're talking about our nucleophile coming up and attacking the, what we call the active carbon is one that has the leaving group. It makes more sense that it's gonna be a lot faster for it to get to the carbon when it doesn't have all these other things around. Let's say if we use the analogy, your nucleophile attacking the active carbon is like throwing a dart and hitting the dartboard. Adding all these other things around is like if you added a whole bunch of other people standing between you and the dartboard. Could still happen, but if you're in a busy bar playing darts, you better be very careful about when you throw that, right? So the more stuff you have around, the slower the reaction's gonna go. Because it has to approach from the back. So we call that backside attack or backside displacement. It's not gonna go through route number 1. Like basically, it seems like there should be some probability. It's so statistically improbable that it goes through route 1 that we can basically say it's impossible. We're talking, 1 out of every million molecules might go that route. And I might even be underestimating the numbers there. So while technically, yes, you can go through route 1, route 2 is so heavily preferred, we basically ignore route 1.
I mean, in route 1, even if it wanted to go that way, wouldn't it get pushed off anyways?
Well, it does create more of like a battle.
Yeah.
And if you look at it in this case, the other way to think about this is in terms of orbitals. Remember when we talked about anti-bonding orbitals? They were like the not stable version of an orbital, right? Where the phase, you got destructive interference instead of constructive interference.
Words are ringing bells, but that's it.
That's okay. What I mainly want you to think of is, remember this, there was this graph where we said, okay, well, that's a sigma bond. If this was our sp3 orbital and an sp3 orbital, when we brought them up together, they overlapped to make a sigma bond. But there was also a way that they could overlap backwards, where the red and where we had red and blue pointed towards each other instead. And instead of getting a positive, all right, positive's the wrong word. Instead of getting a favorable interaction, you got an unfavorable interaction. If you look at that unfavorable interaction, we call the anti-bonding orbital. So as long as we had electrons down here in the bonding orbital, it was stable and it stayed that way. But if we start putting electrons up into this orbital, that's gonna make it less stable. That's gonna make the whole situation less stable. And that's effectively what your nucleophile does. Your nucleophile brings electron density up to the backside of this carbon, where it has this anti-bonding electron density or orbital shape. And as you start bringing electrons into that space, you make this whole situation less stable. Basically, by coming up from the backside, you wind up breaking this bond at the same time, effectively pushing your leaving group away. Right, so all of this is to say, I'm not going to ask you to draw this graph. Anti-bonding orbitals will come up in a lot of, it'll make a big difference when we start talking about alkenes later. But for now, I just want you to know that there is both the experimental evidence showing that we only get one of these sites gets attacked, and it matches, but with both our understanding of sterics and our understanding of orbitals. So in chemistry in general, in science in general, there's often a disconnect between the theoretical groups and the experimental groups. The experimentalists are the ones that just do stuff and measure what happens, and then try to apply theories to explain why things happen the way they happen. The theory-based groups are the ones that start from the idea of, well, we don't have a way of measuring this, but our math predicts this to be true. And sometimes the experimental groups and the theoretical groups disagree with each other usually because there's some variable that one or the other hasn't taken into account. This is a case where both the experimental groups and the theory groups agree that this is our best explanation. All right, so we're gonna stop there, take a break. We'll come back at quarter after at 11:15, and we'll talk about this and what this actually looks like in terms of the stereochemistry.
Okay.
I'm gonna get some water.
So I'm gonna have to give you the stuff that you're gonna say for the club, cause I'm not gonna be able to attend. Did he not read that you can't do this until it's no, it's fine. I talked to him yesterday about. Yeah, I tried to.
So is it this Wednesday or next Wednesday?
I don't know.
Okay, I need food. Come on. No.
I need to tingle too, but I.
Let's go first.
Okay.
substitutes right now. We're not doing this.
He will survive.
I know.
Hot Pockets. Breakfast champions.
Well, okay, I had boiled apples for his.
Hot Pocket sounds better.
She's so weird.
I eat apples a lot. I like boil them for a few minutes, like 10 minutes. And then I put them in a bowl with whipped cream and honey and cinnamon, and they're very, very yummy.
I mean, if you're into that sort of thing, I can't do cooked fruit. I don't like
you-
pies. I don't like anything with cooked fruit,
No,
so.
I like cooked fruit and veggies.
Did you see the note Vagrant's giving me?
I heard about it.
It now lives in my mall, so.
Perfect.
No, so cute. So did you talk to her when you felt like you were stuck?
I don't even know. I was so stressed that night and I was dancing with all the kids and she's like, how are you? I'm like, I'm stressed. But if I fail, I'll just make Riley fail the next day, so it'll be fine. And she was.
All right. Let's finish talking about SN2 reactions. Well, we're never done talking about SN2 reactions. They will be with us forever. But. All right, so here's the general gist of how these work. Because it's a concerted backside attack, effectively what you get is you get as your nucleophile approaches, you start making a bond between your nucleophile and then carbon as this bond starts breaking.
Yeah.
Because you're putting electron density into constructive overlap here. You got destructive interference happening here. So this bond gets weaker at the same time this bond gets stronger. So it leads to a transition state that looks. One time I actually try to do that. There we go. We get what's called a transition state, which we know from our potential energy surface is kind of going to be our peak in between our valleys, right? So if it's concerted, it means it's just one step between reactants and products. And that transition state between reactants and products is going to look kind of halfway in between the two. It's not always perfectly symmetrical. It's not always going to be this clean, but in general, just in terms of where the molecules are, your transition state has to be partway between point A and point B. So to use our coming out of the basin analogy, when you get to the top of Spooner Summit, are you in the basin or are you in the Tahoe Basin or are you in the Carson Basin, Great Basin? In both, right? You're halfway in between. You're in neither, but you're in both at the same time. So that's what transition states look like. It doesn't look like either the reactants or the products, but at the same time, it looks like both of them. So what that looks like in an SN2 reaction is as your nucleophile approaches and comes in to make that new bond, and your leaving group leaves and takes its electrons with it, you get this state that is not stable, that's halfway in between the two. Right, and that looks like if you can, so I use the three-dimensional shape works really well for talking about this like it's an umbrella flipping inside out. Right, so if the umbrella started facing this way, as your nucleophile approaches and your leaving group leaves, it's going to flatten out. So if you can picture taking a picture of the exact moment when an umbrella is in the process of flipping inside out, it's neither inside out or right side out. That's what this looks like. It's close to planar. Everything is pretty much in the process of flipping from one side to the other. And so that's why we get that's why it's a stereo-specific reaction. Because if you started with a specific stereoisomer, R versus S, when you go through this, everything maintains its three-dimensional shape, except it flips to the other side. Right, so that's what makes it stereo-specific. Is the fact that it's concerted and you start from one position and it just flips to the other position, like almost like a light, like a light switch is another good example for this. You think of the classic light, if you try to hold it exactly halfway in between, it's not on or off. It's actually, it's not safe. If you've ever done that before, you can hear it arcing inside sometimes. Maybe that's just my house's wiring.
I haven't heard it, but it's like it doesn't like to.
It doesn't
stay
like to stay right there, and if you keep it right there long enough, sometimes you can hear a little pop.
Oh,
And that's actually the voltage arcing inside there, because you're like keeping it from being in either position.
interesting.
Right, and so the way that we designate a transition state on the potential energy surface, well, one, it's gonna be a potential energy maximum, or it's a also what's also called a saddle point. Because if you think about the 3D shape of going through a mountain pass, it's gonna be a maximum in one dimension. But then if you think about the other mountains that are up above either side, you're at the lowest point in that dimension. Right, because when you make a pass between two places, you don't go right over the top of the tallest mountain, right? You take the lowest path between all the mountains, which is still gonna have a potential energy maximum. So they call that a saddle point because it's shaped like a saddle. Saddle is curved up front to back, but it's curved down side to side, right? That's what this looks like. It's
Going-
curved down here, but it's curved up. If you look at coming into the board and out of the board.
Oh.
Always helpful when we have equestrian themed vocab words, right?
I mean, that's not where I thought you were going with that. I just thought it was gonna be like, yeah, your saddle's your on the highest part of your horse, but also like if your horse lifts his head up, his head is now higher than your saddle.
Right, think more about the shape of the seat itself. All right. So the way these reactions work is we're gonna be replacing one nucleophile with a stronger nucleophile. Because if you have two different nucleophiles, one of them is gonna be better as a leaving group and one is better as a nucleophile. And so we can predict which side of a reaction is favored at equilibrium by just knowing what these pKa values are. So if you have bromide as your leaving group and hydroxide as your nucleophile, there's a huge jump. There's like 23 pH units between those two, which means your equilibrium constant for that reaction is gonna be somewhere in the ballpark of 10 to the 23.
Oh, wow.
It's gonna be both, because remember, pKa is a log-based scale, right? So bromide's such a good leaving group, and hydroxide is a bad leaving group, which makes it a good nucleophile, that it's gonna favor the products very strongly. If it was something else, like if we tried to replace bromine with chloride, we can do that because bromine is a better leaving group than chlorine is.
Yeah.
But because their pKa's are so close, your equilibrium constant might only be 10 to the 2.
So if it had the option of something that was more electronegative, it would take it.
Exactly. So if there's anything else still in there, that's more, a better nucleophile, that's gonna react. First is the wrong way of looking at it, because we're not talking about rates, but it's gonna react with that preferentially. All right, so let's try and do this with stereochemistry involved.
Okay.
If we had this molecule if the leaving group is sticking out towards us, where is the hydroxide gonna approach?
Away from us.
From the backside, right? So basically what's gonna happen is the chlorine pops off and you attach the hydroxide sticking into the board. Which, since in both cases, the chlorine is the number one priority and we're replacing it with the oxygen, that becomes the number one priority. So it actually, if we started with 1, 2, 3, and the hydrogen is into the board, we started with S. And what it turned into, which stereoisomer? Is it still S or did it flip?
It flips because that's now gonna be our number one, right?
Because that's our new number one,
If it's in the back, then it's gonna be opposite.
right? So it still looks like 1 to 2 to 3 counterclockwise, but it's opposite. So we step through. So we started with it in S, we get R. With
Would
it,
you look at that?
would you look at that, with a really high degree of specificity? With like probably closer to like 100 million to 1. Generally speaking, the limiting factor is how pure is your starting material compared to what you get, because it's gonna stay really preferentially favoring that flip, that umbrella flip. Would you also hear that called an inversion? Which, another good vocab word for you too. Inversion means flipped, right?
It means gymnastics, Bradley works at.
Exactly. All right, so how about down here? Does this, that's a stereo center as well, but it's not the active carbon, right?
Right, because the active carbon has leaving.
The active carbon has the leaving group. So that means that this stereo center is not going to change.
So it goes from cis to trans.
So it goes from cis to trans, exactly. That one stays the way it is. Our nitrogen is going to come in and attack from the opposite side. So now our nitrogen sticking up. And if your active carbon is not a stereo center, this doesn't matter. Because if it's not a stereo center, if it's not a chiral carbon, then it doesn't make a difference. You didn't start with something that's asymmetric, that's chiral, so your product won't be chiral.
Did you get that from downstairs?
Good. Very tasty. The sweet red from the ofrenda. All right. So we already talked about this a little bit. There's a lot of text on this slide. But it's just saying that the reaction rates for SN2 are inversely proportional to the stability of a carbocation in the same position. Which is another way of saying that if the carbocation is more stable, that means it's slower in an SN2 reaction. Because it's easier for your nucleophile to come up and attack the carbon when there's nothing else in the way.
Right.
Right, as we already discussed. So methyl chloride is more reactive than, I don't have these in order, so so here, this one's gonna be our most reactive.
Well, yeah, the chlorine would be 2, right? Because bromine's gonna be more electronegative? Or it's
Bromine is
it's-
not as like, it's a better leaving group. So out of these two, the bromine is more reactive.
You just said they're not in order.
I did say that because I was expecting one of them to be, I didn't look at my molecules closely.
Okay, so the bromine is a better leaving group, therefore more reactive.
Correct.
Okay.
And usually that matters less than the primary versus secondary versus tertiary. Right, that it is sort of a balancing, so it's balancing act because there's two variables at play. How good is your leaving group and how much other stuff is in the way? And so those are kind of competing variables. But in general, primary versus secondary versus tertiary matters more than what your leaving group is, as long as your leaving groups are close to the same strength of a leaving group. And for these halides, they are. Those are all relatively close together. So we already talked about this one a little bit. What's going to happen, though? Normally I have more time in this lecture for talking about the test because usually there's more to discuss, but you two killed it, so. So we would expect this to be the slowest reaction. Problem is, that's not what we actually observe. It has 3 methyl groups.
Oh, it does that.
But what they found out is that when you do it with a tertiary active carbon, it's only a first order reaction. It's not a second order reaction anymore. So SN2 reactions follow this. But then something else happens where it goes from being concerted to stepwise. Because remember all the way back. Oh, I did. If it was second order, the nucleophile made a difference, right? The concentration changed it. What they see is with these tertiary leaving groups, or leaving groups on a tertiary carbon, is now all of a sudden the nucleophile concentration doesn't matter. So it tells us a different mechanism is happening.
Is it not one of the two that we know?
It is one of the two that
Oh,
you know, it's just the other one.
Just the step.
Exactly. Because if you make it so that when your leaving group leaves, you get a stable carbocation, then your leaving group leaving can actually happen. Your leaving group leaves and you make an intermediate. That would be, so it would look like if we started with methylpropane, chloromethylpropane, and your chlorine leaves, you get a tertiary carbocation. Remember that a tertiary carbocation is pretty stable actually, as far as carbocations go. So even though the SN2 reaction goes much slower, the first order reaction kind of takes over instead if it's a tertiary carbon. And that one is not SN2 anymore. If it's first order, it would be SN1. So basically we have 2 substitution mechanisms and they can both happen. If it's a methyl with a good leaving group, it's going to be SN2 100% of the time. If it's secondary, it's still going to favor SN2. We'll talk about how we can play around with that a little bit. If it's tertiary, it has to go SN1. If it's going to go through a substitution reaction, it's going to go through the first order substitution.
Because the carbon would be overwhelmed if we did it as an SN2, right?
Exactly, there's too much other stuff in the way.
Yeah.
All right. We're gonna end there and talk about SN1 in more detail on Thursday.
So the lab that we're doing today said that it was due last night on campus, by the way.
It was scary.
Sorry, I will change that. We're doing the steam distillation one,
Steam.
or the lemon oil or clove
Yeah.
oil.
It was just like, lab due tonight. I'm looking at this lab and I'm like, what is this lab?
That's the one that we canceled. I got rid of lab 5 because it was a 2-week lab
Yeah.
and we used the time last
That's what
week
it
instead.
said was it was the 2-week one.
Yeah, so that's on me. I'll fix that so it doesn't show up and panic you.
No, that's fine. Well, it didn't panic
Because I was
me
like,
'cause
how do
knew that
I
we
work
didn't
on
do
this
it.
lab? Like, what, like, is this a different one he gave us and it just looks different online? Like, what is happening?